It is 20 nanometers width and approximately 7 nanometers depth. Now, maybe you're wondering how we plan to make our device magnetic. Well, we are going to do this adding an iron oxide magnetic nanoparticle to our device. In order to bind them together, we will functionalize the nanoparticle with a compound called active.
This compound in an aqueous solution gives our nanoparticle a positive charge, which gives us the possibility to bind it to a negatively DNA device.
And here is where the hollowness of the device comes. If you remember, I said in slides before that the device was hollow. It is because the nanoparticle will be ideally placed inside the box.
Now, when it comes to the experimental work, we did several things that may be divided into two separate things. One of them is the construction of the bots using the different DNA fragments, and the other part will be the correct functionalization of the iron oxide nanoparticle.
As we work with 4 different scaffolds, each double-stranded, we were thinking was it better to work with them together or separately. That's why we made 2 experimental strategies. The first experimental strategy works with the scaffolds separately, while the second works with them together.
After a few tests, we came to the conclusion that the good experimental strategy was actually the second one, which is having all scaffolds and staples in one single folding reaction. So now that we found the best experimental strategy, we made a temperature gradient to find the best optimal temperature for the device to be constructed.
Our optimal theoretical temperature is 63 degrees that was calculating using a melting temperature calculator. In our case, IDT DNA calculator. Also, in order to have more results, we decided to test 2 more temperatures, that is 5 degrees above and below the optimal theoretical temperature.
Now, we're going to give you a brief summary of our results. One of the first things we did after designing the device, we made a simulation to see the fluctuations. We used a software online called Candu, I think it is pronounced that way. And what Candu gives you is a modeling of the different fluctuations that can be found in the device. So as you can see, the fluctuations are in fact really small. They only range from 0.1 nanometers to 0.4 nanometers. So when we saw that the fluctuations were really small, we thought that it was stable enough to be worked with.
And now we present AFN micrographs. These micrographs are from the fusion reaction at a temperature of 58 degrees. These micrographs, it were like a high seen for the first time. If you can observe, there are two structures classified as A and B, and we think that this is our device because the dimensions are similar to the ones of our design.
We also got results from the temperature of 63 degrees, but we didn't put them in the presentation because we actually didn't get any good results from the temperature of 63 degrees. So we're going to skip it and we're going to go to the one of 68 degrees.
Here, if you can see, there are as well 2 micrographs, classified as figure A and figure 1 and figure 2. In figure 1, the absorption time into the mica of the sample was 2 minutes. However, it was very concentrated, and in order to have better results, we reduced the absorption time to 1 minute.
So from this image, from figure 2, we selected 6 different structures randomly to measure them using a software called SPIP. And what SPIP gives you are graphs that show the length and the height of the structure in nanometers. You cannot see here the numbers, but basically they all show a similar size and structure. They all range from 7 to 9 nanometers in depth, which is more or less the depth that we were looking for, of 7 nanometers. And as you can see, in these structures there is shown some sort of depression that we think is actually the whole size of our device.
And now we present the functionalization of our nanoparticle. There are 2 micrographs obtained with them. The first image presents the uncoated iron oxide nanoparticle, while the second image you can observe clearly that there's a code surrounding the nanoparticle, and that code we think is the active.
Now, in conclusion, this is several things that we achieved in this project. We designed a device in CAD Nano and actually proved its structure and stability with different software such as Candu.
Also, we were able to provided it to the AFM.
We also found the optimal temperature for the device to be constructed, which is, if you can recall, is 68 degrees, and the best way of constructing the device with the different scaffolds.
And finally, we were able to functionalize the iron optic nanoparticle with APTIS.
Now, in order to fully fulfill this project, we have some things in the list of future work. One of them is to check if the interaction between the nanoparticle, the functionalized nanoparticle, and the device is actually, that can be actually made. And the other one is to check if the main application is actually possible, that is the isolation of biomolecules.
And now we hope you enjoy our presentation, and we are very thankful. And do you have any questions?
Yes.
Why did you decide to use multiple scaffolds for single-stranded extensions rather than just extending staple strands?
We thought that it was easier because, well, when doing the design in CAD Nano, well, we just found that it was easier to use different scaffolds and just having having the ends of those scaffolds hanging out. But I think that it might be actually a good idea to try if it's actually because, as you can see, when you use the strands, the ends of different scaffolds, you have like maybe some sort of limitation. So I think that maybe it will be a good idea to actually use not only the ends of scaffolds, but also the ends of staples. But yeah, it was just a design decision that we made in that moment. We just thought that it would be a lot easier, but we actually didn't think about having the staples, well, use the staples as a single strand such as the scaffolds.
Okay, and your scaffolds look like they range from about 100 base pairs to about 800. How did you get those synthesized?
There are, excuse me, what?
The scaffolds look like they were ranged about 100 base pairs to 800 base pairs. That's
Uh-huh.
what you had on the slide. How did you get those synthesized?
We actually bought them because we were actually searching a way to use if we could get maybe DNA from some bacteria or something, but because we were searching we were looking for a really how do you say, a really specific design. In this case, we had to synthesize the DNA. Like we have to ourselves. We made the sequences and have them bring them to make all the experimental lab work.
Thank you.
Where did you buy 800 base pair single-stranded DNA? Is that possible?
Yes, it actually is. We bought them from I don't remember the name of the.
IDT DNA.
We actually bought
G
them.
blocks.
Okay.
It's double-stranded DNA.
Yeah, it's double stranded.
So if you bought it as a double-stranded DNA, how did you then generate a single-stranded DNA from?
It's actually a.
We use the thermocycler in order to measure the DNA, so we could fold,
Separate?
to bind the staples. We use the thermocycler to measure the DNA, and also in the folding reaction, we had all those staples and all those things in order to make the device to bind them together.
Yeah, I see.
Thank you.